This is lesson 5.3, binomial probability distribution. Now, binomial probability distribution, what it does is allow us to deal with circumstances in which the outcomes belong to two relevant categories, such as acceptable or defective, or survived or died. The most common ones we use are success or failure. Okay. Now, there are certain requirements in order for it to fall into binomial probability distribution. The first one is you have to have a fixed number of trials. So you have to have a set number of trials that you're going to do. All the trials have to be independent of each other, meaning this one does not affect the next one, and this one does not affect the next one, and so forth, okay? The outcomes have to fall into two categories, success or failure. And there has to be equal probability of success in all the trials. Now, the reason why that's an issue is because let's just say you're a salesman and you're visiting 15 homes for the day, and your approach for the first 10 is the same because you're enthusiastic, you have hope of selling something, but when all 10 of them reject you, all of a sudden you're just deflated, right? And so you don't approach the next 5 doors with the same enthusiasm, or maybe you leave some things out. I know sometimes when I'm teaching the same lesson for 6 classes in a row, by the time I get to that 6th class, I'm just like giving them the bare minimum sometimes because I'm just like done. I'm sick of repeating myself. You know what I mean? And so that change means that you don't have equal likelihood of selling your product, and therefore you don't have equal probability of success in all the trials, okay? And that's why that rule has to be there. Now, this right here, these are notations that we need to know. I kind of wrote this a little bit low by accident, but the probability of success is represented by lowercase p. The probability of failure is 1 minus p, which will be represented by q. N represents the number of trials done. X is the number of successes. Now, success we usually think of as something positive and good, but success is not necessarily positive or good in probability. It's just what we're looking at, okay? And finally, the probability of success is the probability, or probability of X is the probability of getting exactly X successes. Alright, now I have those up there, but I have to erase them in order to do other things. So note that this is going to be sampling without replacement, which means these are dependent events, which fails the independent rule number 2. But because all of these are going to be within the 5% rule that we discussed before, we can use the shortcut of independent trials, and we can say it's independent, okay? Even though technically these will be dependent. All right. The 5% rule. Now, a randomly selected adult has a probability of 0.85 of knowing what Twitter is. Guys, no lie, I've heard of Twitter quite a bit. I kind of have an idea of what goes on there, but I don't know anything about Twitter. I've never used it. So I would fall into the percent that does not know, okay? Now, find the probability of 3 of the 5 random adults knowing Twitter. So find the probability of, I'm just going to write it the way I would normally write it, the probability of 3 out of 5, okay? Now guys, I'm not going to find the actual probability right away. First off, we're going to discuss whether or not this is binomial probability distribution, okay? So let's go over the rules. The first rule is there a fixed number of trials? Since we're selecting 5 adults, that is a fixed number, so yes, it passes the first rule. The second one, the trials have to be independent. Well, since you're asking 5 different adults, the first adult's answer does not affect the second adult's answer, so therefore they are independent of each other. The next one, each trial, this is the third rule, each trial must have all outcomes fall into 2 categories. Success or failure is the most common. In this case, it'll be do they know or don't they know, right? Yes, they know, no, they don't know. So yes, it has 2 categories, either yes or no. And finally, the fourth one, the probability of success remains the same in all trials. Since we're asking 5 different adults, that probability of 0.85 is the same for each adult. So it passes all those rules. This is binomial probability distribution. Now, going on, we're going to next identify what NXP P and Q are. So N represents the number of trials. We're asking 5 adults, so N will be 5. X represents the number of successes we're looking for. We're looking for 3 successes, so X will equal 3. P, we know the probability of success is 0.85. Q is the probability of not having success or failure, which means they say no. And so that right there would be 1 minus 0.85, which is 0.15. So my Q is 0.15. Alright, now I know what my values are that I need in order to solve this. Let me give you a formula now. I'm going to have to erase this. Keep this in mind. Hopefully you have it written down so that you know what I'm talking about as I fill in numbers here in a minute. But here's my formula for probability. The probability of success is going to be n factorial over n minus x factorial x factorial. This should look familiar to you. If you were to replace x with r, then this would be the formula for combinations, okay? But that's not all we're doing. We're going to multiply this by our probability of success raised to the x power times the probability of failure raised to the n minus x power, okay? So this is the formula that we're going to be using. And I'm going to show you exactly what this all means, so don't freak out about it. But let's go ahead and solve this. So, given that the probability is 0.85, that people know what Twitter is, find the exact value for the probability of 3 of them knowing. So basically, guys, this is P of 3. Notice that 3 is in place of x, so every time I have x, that's where 3 is going to go. N, we already identified before that n is 5. So this is 5 factorial. N minus x would be 5 minus 3 factorial, which is 2 factorial, right? So I'm just going to write 2 factorial right here. And x factorial is 3 factorial. Times, now P is the probability of success. That was 0.85. Raised to the x power, which is 3. The probability of failure, that one was 0.15. Remember, we found that by subtracting 1 minus 0.85. Now it's n minus x power. We know that to be 2, right? So raised to the second power. Alright, when you solve this all out, guys, here you do 5 times 4 up here, and you use 2 to reduce the 4 down to 2, so this will give you 10. You know, you can work this out with your calculator, right? Don't forget to raise these to the powers before you multiply all this. When you solve this, the answer that you will get is 0.138 rounded. Basically, that means there's a 13.8% chance that the person will know what Twitter is. That exactly 3 people will know what Twitter is, okay? Alright. Now, let's go back to, we talked about a study that showed people believing in the devil. And in that study, they told us that the probability that someone believes in the devil, or an adult, sorry, is 0.6. That means the probability of failure is 0.4, right? 1 minus 0.6 is 0.4. We're going to use 5 people in our trial again. We want to know the probability of success for choosing exactly 3 people. Okay, so we're going to use this to solve for the probability of 3 people believing in the devil. So probability of 3 using the formula we just used. Well, the combination formula is going to be identical. My n is 5 factorial. Remember, we're plugging it into the formula we just had. Then right here we had 5 minus x. 5 minus 3, which was 2 factorial. And then right here, this is the x factorial. 3 factorial. Times. Now this is what we're going to get a little bit of change on. My probability of success is now 0.6. My x is the 3rd power. Times My probability of failure is 0.4, and that is going to be raised to the 5 minus 3, which is 2, second power. Now guys, you can use your calculator to solve this all out. Don't forget to do the powers first before you can multiply things. So 0.6 to the third power, 0.4 squared. And when you finish solving this out, you should find that your answer is going to be, let me find my answer here, 0.346. That means you have a 34.6% chance of having exactly 3 people out of 5 believe in the devil. Okay, that's according to that study. Now, we want to find the probability of at least 2 believing in the devil. At least 2. I'm going to write that down just so we can, I'm going to keep these numbers here. But at least 2. That means the probability of 2 people knowing, the probability of 3 people knowing, the probability of 4 people knowing, and the probability of all 5 knowing. We would have to take all those probabilities and add them together. So you could choose to do that if you want. You would have to do that same formula for 2, 3, 4, and 5 and get those different answers and then add them together. Or you can do my way, which will be a little bit shorter, and that's to first find the complementary, which is the opposite of that, and then subtract 1 from it, or subtract it from 1. I'm going to do that, okay, because that's going to be easier. I only have to find 2 probabilities that way instead of finding 2, 3, 4, and 5, which are 4 different probabilities. Okay, so if it's at least 2, that means the opposite of that would be 0 or 1. So I'm going to find the probability of 0, and I'm going to find the probability of 1. I'm going to add those together and then subtract 1 from it, or subtract them from 1. Okay, here's how we set this up. There are 5 people in the trial, 5 factorial. This spot right here is for 5 minus x. 5 minus 0 is still 5 factorial. This spot right here is for x factorial, 0 factorial. Now, I know guys that you're going to think that 0 factorial is 0, which means this would be an undefined problem. But when we have factorial, 0 factorial actually equals 1. Don't ask me why, I don't know the reason for it, but just know that 0 factorial equals 1. Times 0.6 raised to the x power. My x is 0. Any number raised to the 0 power is automatically going to give you 1 as an answer. Okay? So basically this is 5 over 5, which is 1. This is 0.6 to the 0 power, which is 1. So these multiply out to be still 1, times 0.4 to the 5 minus 0 power, so to the 5th power. The answer on this one is basically going to be 0.4 to the 5th power. And that's going to be your answer. It is 0.010 rounded. Okay? Now, the probability of 1. Again, it's 5 factorial on top. This spot is for 5 minus 1, which is 4 factorial. This spot is for 1 factorial. 1 factorial is also equal to 1, guys. So 0 factorial and 1 factorial both give you 1 as an answer. Times 0.6 to the 1st power. That means that it's going to give you 0.6. Times 0.4 raised to the 5 minus 1, which is the 4th power. Again, don't forget to do your powers first, then multiply these out. Your answer for this one is going to be 0.077 rounded. Now guys, I'm going to add these two together. When I add 0.01 and 0.077, you get 0.087. Now guys, this is the probability of not getting at least 2. So to get the probability of at least 2, all this has to add up to be 1, all these probabilities, so we can solve now for the actual answer, which will be 1 minus 0.087, and that gives us 0.913. That's the probability of at least 2. You guys, I hope you understand kind of what I did there. I did the opposite of what it asked for because the opposite was going to be easier. And then I subtracted the answer of the opposite from 1 to find the probability of at least 2. You guys, if I found the probability of 2, then the probability of 3, the probability of 4, the probability of 5, if I found all those probabilities and added them together, I would get 0.913. So this was just an easier way of doing the same thing. Okay. Now guys, there's an actual table. You can look at it in your book. The table would have shown you that the probability of 0 at 0.6 would be 0.01 and at 1 would be 0.007. You could have added those together and subtracted them from 1 and it would give you the same answer. I can't really show you the table too easily because of the book, and so we'll just let you see that for yourselves, referring to table A1 in the back of the book, and I'll let you look at that. Okay, that's that.